Okay, good afternoon, everybody. So I'm going to talk to you about the new concurrency features that were added to C++20 and some possible future directions for which we've currently got papers in the pipeline, or at least ideas of papers. And hopefully, obviously, those will then become part of future standards. So, and C++20 in general is a huge release. There's loads of extra features. We've got concepts finally, which is going to have a big change to the language, and there's all sorts of things. But some of those additions are concurrency features. So I'm going to give you an overview of what those are. They start with cooperative cancellation, which is something that we've actually wanted to have in the thread library since C++11, but we've now finally got it in the C++20 draft, so I'm very excited about that. And as well as a mechanism which is independent of how you manage your threads, there's also a new thread class that incorporates that. There's a couple of new synchronization facilities, so I'm going to talk about those. On the low-level end, then we've updated the standard atomic template and introduced a new atomic ref template, which provide us more facilities for those who want to work close to the metal. And then coroutines, which on their own are not a concurrency feature, but they can be used to write concurrent code and to give you performance in doing so. So, with regards to cooperative cancellation, if we think about an application from the outside, then lots of applications have GUIs, and lots of tasks that you do in a GUI have a cancel button. Things that might start a long-running task, I want to render this scene in my 3D modeler, and then say, actually, no, I wanted to change something, click cancel, and abort that. I want to download a file. Oh, hang on a minute, it says it's going to take 5 hours. No, click cancel. Abort that. But it's not just GUIs. If you're running a series of tasks, if you're doing a search and you've split the search into, I've got 1 million elements to search for something specific, I divide that up over threads. As soon as one of them has found the element that you're searching for, you want to stop all the others. Or if you're doing a spell check in the background and the user edits the string that you're spell checking, then you want to cancel the spell check and not leave that running. And most operating systems provide you a means of forcibly terminating a background thread, but that is just a disaster waiting to happen and can leave your program in a completely unstable state. So you want cooperative cancellation rather than forced termination. In C++20, then we have this pair of new classes that work to provide us this feature. We have a stop source and a stop token. Now, unsurprisingly, a stop source is where if you have one of those, you can actually request that your background operation stop. And then the background operation itself will hold a stop token, which it can then query to see, has somebody asked me to stop now? And this is purely cooperative. If the background task doesn't check its token, it will not be interrupted. So, as a general sort of flow of how it works, you create a stop source, you obtain your token from the source, you pass your token to your background thread or background task, and when you want it to stop, you say, request stop. Periodically, your background task will call stop requested. Query, has the stop been requested? And then it will then have to decide, okay, somebody has asked me to stop, so now I'm going to do something about that. And again, to reiterate, if you do not call stop requested, nothing happens. This is purely cooperative. Nothing is forced on you. There is also then an integration with condition variable any. Now, for those of you that aren't so familiar with it, it's standard condition variable is what you use most of the time when you're thinking condition variables in C++. Condition variable any is its flexible cousin. That rather than working exclusively with standard mutex, it allows to work with any lockable thing. And this flexibility allows us to make it work with stop tokens as well. And so you can then pass a stop token as an additional parameter when you wait with condition variable any, and then the wait can now be interrupted if the stop token has been requested to stop. So to put that in context with some code, we have a mutex to protect our data, and the queue, which is the data we're protecting, and our condition variable. And then if you're waiting for some data, then you've got this stop token, somebody's given it to you, and you're running a background task. So we lock our mutex, and then we wait. And we use the form of wait until. We're waiting until either our little lambda tells us that the queue is not empty anymore, or that stop token has been requested to stop. And in this case, then it's going to throw an exception. Say our operation was cancelled, but obviously what you do in any particular case is then up to you. And the return value of wait until is the return value of your predicate that you provide. So in this case, if it is false, then our queue was still empty, which means the reason it stopped must have been because our stop token was set. And then obviously if the return value is true, then we can then process the data. Okay. Somebody has a question? Yes, if you go to the microphone so that everyone can hear.
Just quickly, you're passing by value. How is the token getting set? Is it assumed that it's going to be moved into that?
Yeah, no, tokens are value handles, so you can just copy them around. And they essentially reference count to an external shared resource.
Oh, it's like a shared, okay.
Like a shared pointer to something. And in fact, in the open source implementation that we've got, then it is a shared pointer to something.
And just because I'm looking up, I can't remember, wasn't the condition variable semantic before was you would do a while wait until, or while wait, and then you'd have to recheck if your condition was still true and go back into the while?
So,
in C++?
Yes, if you're used to POSIX condition variables, then yes, you would recheck your predicate. If you pass the predicate to the wait function, then the library will do that for you. There's also an extension with stop callback. Stop callback allows you to say, here is a stop token. When somebody has requested to stop this requested stop with this token, I want you to call this other function. And that allows you to interrupt other things. So if you have some async I/O, and you have a function you can call to interrupt that I/O, which on the slide I said is called cancel I/O. If you have such a function, you can then use that with a stop token by wrapping it in a stop callback like this. And then if the token is signaled, it will cancel your I/O operation. And so the read data, which would normally be a blocking operation, can now be cancelled by somebody requesting stop, as opposed to the rest of the world having to know that it's an I/O operation that's being interrupted. Yes, there's a question.
Does the stop callback only apply for the lifetime of the stop callback object?
Yes, the callback is only alive for the lifetime of that object. So as soon as the stop callback object is destroyed, then the callback is no longer registered. So we have this new thread class. The new thread class is called a JThread, and it integrates with our stop token to support cooperative cancellation. It has an integrated stop source that is wrapped inside the JThread object. And then when you destroy the object, it automatically calls request stop on that stop source and then joins with the wrap thread. And so this means that then you can use it to cooperatively cancel your background threads when you destroy the object. obviously the thread that needs to check the stop token in order to deal with this cancellation request. And so this stop token is passed as a first parameter to whatever functional callable you pass for your thread. So we construct our JThread object, we pass it thread func, we give it these additional arguments, some string and some number. Then the function itself is called with a stop token first, and then the additional arguments. It is backwards compatible. If you don't support having the stop token passed first, you can still use it just as a drop-in replacement for standard thread. So if you had a thread function that just took a string and an integer, then that would still work in this case. But obviously it wouldn't now have the stop token so that it couldn't check whether somebody had interrupted it. And then obviously the purpose of having this stop token is that you're going to periodically check it. So we have our while loop here. While I'm not being asked to stop, then I'm going to keep doing my stuff. And then obviously at the end of foo, then the destructor for JThread is called. And this will request that the operation is stopped and then wait for the thread to finish.
And so that means previously, like a thread, standard thread, would just continue on its merry way, detached. But now we have JThread, which will, on its destruction, cause it to join.
So the JThread will, yes, it would in the destructor call it to join. If this said standard thread, then when you hit the destructor, if you haven't explicitly joined or detached, it will terminate your program.
Terminate, right, yes.
So this is more of an RAII style way of dealing things than with standard thread.
Cool, but does that mean if I didn't, this will signal to the thread to actually specifically stop at the close of the scope there?
Yes, it does, yes.
And if I wanted it to keep going till it was completed?
Then you'd have to transfer your JThread handle somewhere else or explicitly detach it. So yes, I mean, JThread as an object is movable just like standard thread, so you can return it from your function, you could store it in a vector, you can keep it alive by whatever means necessary until you want that thread to finish. Okay, so as well as our cancellation support, we also have new synchronization facilities. There are 3 of those. We have latches, we have barriers, and we have semaphores. Latches are single-use counters. And so they start at some specified count, which you provide to the constructor, and then they count down. And when they hit 0, they are signaled, and they stay signaled. They latch. The count are any thread may count down the latch by any amount, as long as, if it's only got a count of 5 and you try and count it down by 42, then that's not going to work. But as long as there's enough count left, you can decrease it, and then when it hits 0, it's signaled. Any thread can wait for it, obviously before or after it's been signaled. And as soon as it has been signaled, the waiting threads become unblocked, and they return from their wait, and they can carry on. So to put this in some code, we have our thread count of whatever. We have our latch that we construct, specifying the number of threads. Then we've got some data that we're going to generate. We're going to populate this array of data with, by each of the threads. And then we've got our array, a vector of JThreads in this case. And so we start our threads, and each thread is going to generate its own data with this make data function and populate the corresponding element of the data array. When it's generated its specific set of data, it's going to count down the latch and then carry on doing other processing. So we're not waiting for the threads to finish, we're waiting for the data block to be populated. And then at the end, obviously when we started all our threads, we can wait for them all to finish, do their data, and then we can process this data in some fashion. And obviously the threads will then continue until the end of the function when the destructor of the vector destroys the JThreads, which will then wait for them all to finish. So note that in this case, then the thread function doesn't take the stop token, it doesn't check, we're just assuming that it's a straight line, we always want it to do its processing. And one of the primary uses that I find for latches is actually for testing multi-threaded code, because it allows you to set up all the threads in your test scenario as close to where they're going to invoke the code under test as possible. So you can start each thread and do its setup and initialization, and then have it wait on the latch. And then when all the threads have done their setup, then they're all released, and then they can all carry on and actually do the code that's trying to test whatever it is. And so this in the example, would use the combined arrive and wait call, which you could write as the code to count down the latch and then wait, but there is this combined arrive and wait because it's sufficiently common use case that threads that are involved in some group operation both want to say, well, I'm ready now, but I'm going to wait for everybody else to be ready. So the second of the three additional synchronization tools from C++20 is barriers. Now, standard barrier is a reusable barrier, and it essentially provides sort of what's referred to in the standard document as phases. So you construct your barrier, and you specify the count, and then a completion function, which I'll talk about in a second. And then it starts the first phase. And in any given phase, you're waiting for a number of threads to arrive at the barrier, and that number is the number you specified in your count. And when these threads arrive at the barrier, and then they wait for the barrier to be signaled. And then when the count reaches 0, then the barrier, we start the end phase, so at the end of our phase. And at this point, the completion function that you supplied is now run on one of the threads that arrived at the barrier. You don't know which one, so if there were 10 threads involved and they all arrived at the barrier, then one of those 10, but as I say, it's unspecified which and may vary from each loop to loop, one of those will run the completion function. After the completion function is called, then the count is reset back to the maximum, and the next phase begins. Now, this is great for things where you're doing a series of tasks which are essentially the same, and so you're running it in a loop. And during each task, there are bits that you can split up into parallel parts. So you have your threads that are doing the parallel parts, and they all do their tasks, and then they wait on the barrier. And then you can have a single-threaded bit that gathers together all the data that they've all been working with and does something to it. So if you're rendering video, then you might have the different threads do different parts of the frames in some fashion, and then when they've all done their bit, then you've got a complete frame and you can ship it out. And by synchronizing with the barrier this way, then the single-threaded completion runs before they resume their next step. And so that means there aren't some threads that have started rendering the next frame before it's been finished shipping out. It provides this double synchronization. So yeah, so if you've got multiple steps, so if your grand processing has multiple steps, then you might actually be able to have each section encapsulated. So we have the first bit, which we can do in parallel, then the completion function passes the result of that onto the next stage in the pipeline, and then the threads involved in this part start the next step on the next bit of data, while other threads then proceed with processing the data that we've passed on from the first time through. So again, just to put this in context with some code, we construct a standard barrier. Now the template function here, the template parameter is the type of the completion function. It fundamentally has to have this signature, essentially void with no parameters, but it doesn't have to be standard function. It could be a function pointer. It could be a concrete type of your choosing. We specify the number of threads and the actual concrete instance of the completion function in the constructor. And then we have our thread that it's going to do some stuff, it's going to arrive at the barrier, and then wait until its next iteration. And when all the threads involved have arrived at the barrier, then again, our finished task function will be called. Okay. The final of the 3 new synchronization facilities is Semaphores. Now, Semaphores are fundamentally actually quite a low-level synchronization facility. And in principle, at least, you can build just about every high-level synchronization thing using only Semaphores. You can build a mutex with Semaphores. You can build a condition variable with Semaphores. You can build a latch or a barrier with Semaphores. So conceptually, they're quite low-level. And the idea is that a semaphore has internally a number of slots. And you specify this when you create it, you specify what its maximum value is and then what its current value is. And then over time, then threads can acquire a slot, and if the count of available slots is currently greater than 0, then it decreases the count. And threads might release a slot, in which case it will increase the count. If the count is 0 and you try and acquire, then you will block. Or fail if you're using a try-acquire operation. And likewise, if you release a slot and the count is currently 0 and there is a thread blocked for it, then it will release that thread so that it can acquire the value, acquire a slot. But though conceptually you might want to imagine that there's some relationship between acquire and release, and if you're actually trying to use these for any purpose, then you have to have the logic in your code mean that there is some relation. The runtime doesn't care. You can acquire 3 slots in a row on the same thread and release 3 slots on a different thread. It has no direct relationship, unlike a mutex where you have to unlock it and unlock it on the same thread. So yeah, you can use it to build just about anything. There is a book that I have seen on the internet and which I've downloaded, which is actually quite interesting. It's called The Little Book of Semaphores. It is not small. It's a couple of 100 pages. And it tells you how to do just about everything with semaphores. It's really interesting. It's worth a read. It's also worth seeing quite how complicated it is, and aren't you glad that the standard provides all the things directly rather than expecting you to do it with semaphores. So there's also, as a specialized term, then a generic semaphore has some number of slots, whereas a binary semaphore has exactly 1 slot. And so either it has an available slot or it has no available slot. So it's got these 2 states. It's binary. And that is what you would use if you're trying to do a mutex. So in C++ 20, the basic template is a counting semaphore, and you specify the maximum count as the template parameter. And then there is this template alias for binary semaphore, which is an alias for counting semaphore with 1 as the maximum count. And as well as blocking with the acquire member function, we also have try acquire, which will fail if it can't acquire it, and try acquire for and try acquire until, which in the usual tradition of the concurrency library, they wait for a specified duration or until a specified time. And again, they return false if they can't acquire the semaphore and true if they succeeded. So again, let's put this in some real code. We have a counting semaphore with a max count of 5, and we're going to start it with full 5 slots. And then we run our function, we acquire the slot, we do some stuff, and we release our slot. Because we have 5 available slots, at most 5 threads can be calling do stuff at once. So this is obviously like a mutex, but with extended up to 5. If you're trying to do things with, trying to emulate a condition variable or something with semaphores, then obviously the code looks much more complicated. Okay, so for the low-level people who really like to use atomics, we've got some updates. Low-level weighting, in my mind, is one of the most important parts of this update to atomics. And if you're writing lock-free code, then this is really helpful. But given that most people shouldn't be writing lock-free code, then for most people, actually, you can set it aside. We also have atomic smart pointers in the form, so now you can use shared pointer and weak pointer with the standard atomic template. And we have this new template, atomic ref. So for low-level weighting, we have 3 new member functions. We have wait, we have notify one, and notify all. Now, fundamentally, it's a bit like a low-level condition variable. You have your atomic value, and you say wait. And what you do is you pass it the value that you think it is at the moment. And wait will return either immediately if the value is different, or when somebody is notified. And so this allows you to sort of synchronize. If you're waiting for something to be ready and there's a Boolean flag and it's initially false, and you say, wait, false. And then if somebody has set the flag before you call that wait, then the runtime will say, hang on a minute, you said wait, false, but this is already true, so I'm going to return straight away. Alternatively, if it really was false when you called wait, then it will sit there and it will say, okay, I'm going to register with the operating system kernel that you're waiting for this. And then when somebody calls notify, whether notify one or notify all, then it will wake you up. Like condition variables, it might also spuriously wake you up because something in the OS means that it's not quite sure whether or not it's missed a notify, so it needs to wake you up to be sure and to be safe. So you need to take account of that, and you'll need to recheck what the value is when you wake up and make sure that the state that you're waiting for has actually happened. But as a basic principle, it works quite well.
So to check my understanding, so I would be waiting on a Boolean and its value is false. I say wait for it to be true, or
yeah, so
wait for it to not be false.
Yes, you wait for it to not be the value. So yeah, so if it was a pointer, for example, no, you would pass in, you'd read the pointer value, say, well, hang on a minute, that's not the pointer that I want to deal with. So then you wait and you say, well, this is what it was when I waited, and then if it's changed, then it will wake you up.
And when you wake up, you need to check it, sort of condition variable like for spurious, or potentially if it was a true condition when it woke you, but by the time you actually went to check, it changed again.
Well, then it's changed again, and you've got to design your code so that it deals with that scenario. No, this is really low-level facilities, so you need to think about various orderings. It's just a little help to avoid busy spin weights, really. Yeah, there's another question.
No, wait will do the check itself.
It will check when it goes to sleep, but it won't check when it wakes up.
No, it checks it when it wakes up.
Doesn't check when it wakes up.
Yes, it does. I was the final author of the paper. The wait, it says it repeatedly checks when it's woken up. The wait function will check if the value is different than what was specified.
Yeah. So yeah, you
and
can use return values.
It will go back to sleep if the value is still what it was originally passed in.
Okay. Yes. Thank you for that correction.
So I have a question now. So if before the addition of the wait and notify, if the T was atomic of T, was lock-free, it's also going to be lock-free right now. And then size of if before the size of T, was equal to size of SD atomic of T, that's still going to be maintained, so there is no other funny stuff like a condition variable, or.
Yes, I mean, this is probably implementations are not going to want to change the size of standard atomic of T, and they're not going to want to change whether or not it's lock-free. So this will use a kernel mechanism to make sure that it does the waiting. And if they need a separate variable to deal with that, then they'll put it somewhere else in the runtime library, probably, rather than trying to mess with your atomic of T.
Yeah, like a lookup, based on, for example, a hash or something like that, a modulo of the address of the variable, or?
How they do the internals is entirely up to the implementation, and yes, one possibility is to use the address of the variable as some form of hash into an internal table.
Okay, thank you.
So, like condition variables, notify one and notify all wake up either one or all of the threads blocked in wait. Obviously, the set of threads that is blocked in wait is subject to races, depending on the various scheduling of the different threads, so you need to be careful on how you deal with that. Just something to be aware of. Okay, so I said we have smart pointers, we have atomic of shared pointer T and atomic of weak pointer T. Now, see, normally the standard atomic template only allows you to use things that are trivially copyable. And shared pointers are definitely not trivially copyable because you want to deal with the reference count. So we have specializations for this because it's sufficiently generally useful. In C++ 11, you could have managed with free functions. You could say atomic load on a normal shared pointer and atomic store on a normal shared pointer. But these were free functions, and it's easy, therefore, to omit them in some of the cases when you're dealing with something that you want to be atomic. So in C++ 20, then we now have atomic of shared pointer of T, which means you can't forget to use the functions. In common with every other instantiation of atomic of T, it may or may not be lock-free. If it is lock-free, then you could use it in a lock-free algorithm, and it would probably simplify your cleanup code. If it's not lock-free, then I wouldn't recommend using it in a lock-free algorithm because now you've got a lock in there. It's going to have a spin lock. But it might still be a better replacement to using a shared pointer with a separate standard mutex. So if all you were protecting with your standard mutex was a standard shared pointer, then you could now have an atomic shared pointer, and the internal spin lock is probably a teensy bit faster than using standard mutex. But one thing to watch out for, even if it is lock-free, it can be slow under high contention, because the sequence of operations necessary to do a lock-free operation on an atomic shared pointer and keep the reference count correct is quite long and uses several read, modify, write operations. And read, modify, write operations under high contention actually can cause global synchronization, which really slows everything down. So if you're trying to use this as a performance gain, you need to profile, like everything else. Just to demonstrate how you might use it, if you had a stack and you're wanting to share it as across threads, then rather than having plain node pointers and then trying to deal with, or atomic node pointers and trying to deal with the cleanup in another way, you could use atomic of shared pointer, and then you can use the atomic member functions to make it. So if you look at push, then we create our new value shared with make shared. We then load what the old value was, and we use compare exchange to replace the head of the stack with our pointer to our new value. And if it fails to do one iteration, it will then automatically update our next pointer, and then the next time round we hope it succeeds. So when it succeeds, then the head of the stack is now pointing to our new node, and its next pointer is pointing to what was the previous head of the stack. And on the pop side, we can load the head pointer. While it is actually pointing to something, there was a value there, then we can try and compare it, swap that for the next value. If the exchange succeeds, then we've successfully removed our value from the stack, and so we can return the value that's stored in that node. If the exchange fails, that means somebody else has taken the front of the stack off or pushed another value on, and so we actually need to try again. And obviously in this case, at the end, if you try and pop off an empty stack, then it's going to throw an error and say, no, stack was empty. So you could have had it as try pop and return false or something, but obviously that's whatever you do there is up to you. So if atomic shared pointer is lock-free, this is now a lock-free stack. If it is not lock-free, well, it's a thread-safe stack, but you would want to profile to see how it compares to using a mutex and just protecting the nodes that way. And in fact, you probably want to do that profiling anyway, because it's only worth the complexity of the lock-free stuff if it gains you some performance. Yes, there's a question.
If it's lock-free and it's a shared pointer, what if it gets assigned to null and the thing that it's managing has a very slow destructor? How do you run a slow destructor in a lock-free way?
Well, the lock-free operation is the actual change of the pointer, and so the destructor would not be run inside the lock-free part. And yes, if your destructor has to acquire locks or otherwise release resources and wouldn't itself be lock-free, then yeah, you can't use it in this context. But the actual operation on the shared pointer that changes the reference count would be the lock-free part. Okay. And then the destruction of the object would happen afterwards. So the third extra thing for the atomics is we have atomic ref. Now this allows you to perform atomic operations on objects that are otherwise non-atomic. And this can be important when you've got something shared headers with C code, which then obviously can't use standard atomic, or you've got a struct or something where the binary layout is very important and you've carefully selected the binary layout so that it matches something external to your system, but you still want to perform atomic operations. The important thing to note, of course, is that if you're using atomic ref to access something, you can't do non-atomic operations on that same thing. You now have to use atomic ref for all accesses to it, because otherwise the atomic ref part doesn't work. So if you have a C struct and you want to change its count variable with atomic, then you create your atomic ref of int, and you pass a reference to the thing you want to change, and then you can just use the same operations as if it was atomic of the same T. So this has the same operations as atomic of int, so it has a plus plus operator, which does an atomic increment. Yes, question?
You said a statement about how if you use it as an atomic ref, you have to continue to access it as atomic ref. Does that mean all threads throughout the program?
All threads throughout the program until there are no atomic ref objects referencing that thing.
Ah, okay.
And this is a special case scenario. Sometimes it's really useful, but lots of the time you should probably just use an atomic of T instead. Okay, so coroutines is the last thing that's in C++20 that has bearing on concurrency. Fundamentally, a coroutine is a function, but it's something that you can suspend midway and then resume at a later time. And it continues where it left off, and things like local variables have the same value. Well, see, with the benefit with multi-threading is, of course, you can resume it on a different thread. In C++20, our coroutines are stackless, so it is only the local variables that are preserved. In stackful coroutines, it would preserve the entire call stack, but C++20 is stackless, so it's only the local variables in the current function. This minimizes memory allocation, so you can have millions of in-flight coroutines if the little function, the coroutine itself has a small enough number of local variables. And sometimes the coroutine overhead can be completely eliminated. This is Gore's disappearing coroutines trick. So you can have a generator that generates a series of values, and actually using coroutines, and then when you look at the generated assembly language, where's my coroutine gone? It's just returned the sequence rather than actually doing any visible coroutine code. So the benefit from concurrency comes if you have library support, you can wait for something that is coming from another thread, and it will suspend your current thread suspend your current coroutine. And so now the thread has an opportunity, if your library is set up right, to actually do some different new operations on the current thread. And then when the other code has produced the value, then it will resume your coroutine at the point of the co-await. And it can work with something like futures in order to pass the data back and forth. But what we're missing from C++20 is the library support that makes this work. All we have in C++20 is the basic framework. You are looking to third-party libraries to actually do this sort of thing. So there's coroutine stuff in Facebook's Folly and in Lewis Baker's CppCon library that allow this to work with threads. Writing it yourself is very hard. Okay, so that's what we've got in C++20. So what about future standards? Well, there's lots that we could have, so I'm only going to talk about a few things. There's a synchronization wrapper for ordinary objects, which I'm quite excited about, partly because I wrote the proposal. There's some enhancements for standard future. There's executors, which is something that we've been waiting for since C++11. I hope that there will actually be a proper coroutine library support for concurrency. There's proposals for various concurrent data structures, and then there are safe memory reclamation facilities to help you write your lock-free code and actually free up memory in a safe fashion. So, as a concept, synchronized value encapsulates a mutex and a value, which means that you can only access the value through this synchronized value object. So you can't forget to lock the mutex. And it's easy to ensure that the mutex is locked across a whole operation because you can specify an operation to apply, and it will lock the mutex, do your operation, which can be a full lambda or any other function call that operates on the protected value, and then it unlocks the mutex. And it also scales to multiple value operations, so you can say, I've got 3 synchronized values, I want to do an operation across all of them, it will lock all the relevant mutexes, do the operations, and then unlock the mutexes. Of course, I say conceptually it encapsulates a mutex. It might not really have a mutex, it might use alternative implementation strategies to make it work. But from a user's perspective, that's what it looks like. So in code, if you have a synchronized value of a string and you want to get the value, then you apply a little lambda to your string, which returns the value. Your little lambda takes an unprotected reference to the stored value, and you pass it to apply along with the synchronized value object. And then you can do that. And likewise, you could append a value to a string by having, you have a little lambda that, again, takes the value by reference, and then you can add in this extra string that you passed, and then, and that will then be done under the context of the mutex. There is a question at the front here. Yes, it's an overload of apply. It looks very similar to apply with tuples, which was intentional, but it's an overloaded for synchronized value. And it's also overloaded for multiple synchronized values. So if you have 2 strings, then you can, in this case, just add them together and return the result. So you've concatenated your strings, but that is done with the mutexes for both of them locked. And it doesn't matter which way round you specify the strings. If you use a different operation that synchronizes across the same set of synchronized values in a different order, then it all just works. The runtime library uses equivalent of scope lock to make it all work. The Concurrency TS, which actually now is a few years old, specified a bunch of enhancements for standard future. I'm hoping that we will get something like these into an upcoming version of C++, because they are really useful. The first is continuations. The second is waiting for a set of futures, and then finally waiting for one of a set of futures. Now, all of these are generally useful. In the TS, they're in the standard experimental namespace. So that's long for slides, so we use stdexp, standard experimental. The idea of a continuation is something that runs when the first task is finished, and we schedule it with the then member function. So we have we have a future, we say some future dot then my task, and when the future becomes ready, then it will trigger the continuation. In the Concurrency TS, the parameter takes the future by value as a parameter, and because we've now scheduled this continuation, the original future is no longer valid. So only one continuation can be added if you're using just plain standard experimental future. So if we had some function to find the answer that gave us a future, and we wanted to process that result, then we could then say, f.then process result. It also works with shared future, but it must then take the parameter to the continuation must be a shared future, and the source future remains valid. Because you can have multiple copies to a shared future, each of them can schedule continuations, then actually you can schedule multiple on the same source one as well. If you're waiting for things, then if you spawned off a bunch of tasks that do some background things, and you want, as soon as one of them is ready, you want to do something, then you can say when any, then it gives you, then I want to do something. So when any itself gives you a new future that is itself ready when one of the original source ones becomes ready, which of course then you can then use with continuations. And it's great if you've got speculative tasks. Well, I've got 5 different ways of solving this problem. I'm going to spawn off, and I've got enough processing power to spawn off a separate thread for each, but as soon as one of them's ready, then I want to use the result and carry on. Or if I've got some tasks that I want to do, and as soon as any one of them has completed its bit, then I've got some more processing to do, but I don't care which one comes first, and then I'm going to wait for the others. So, it has uses for that. So you spawn your async tasks. When any of them are ready, then you can then process your result. And then do stuff with, again, when you schedule continuations, you get a new future back. So then you can do stuff, you can wait for that continuation with a get, and then do your final stuff with the result of that continuation. When all is a bit similar, except it waits for everything. And it is better than waiting for each future in turn. Because if you wait for each future in turn, then your thread blocks on the first future, then wakes up, then blocks on the second future, then wakes up, then blocks on the third, and you've wasted a load of time slices. Whereas if you wait for everything before you're notified, then it's a minor optimization. And there is a question.
Yes, about that dot then. On which thread the continuation is called?
In the Concurrency TS, it's unspecified. And that's one of the reasons why we haven't got it in C++20 is because we want to pin that down, possibly with support from executors, which is also not ready for C++20. So.
Thank you.
So waiting for all futures, you spawn some tasks, when they're all ready, then you can process the results, and you get another future back. Executor. Fundamentally, it's an object that controls how and where and when a task is going to be run. As its purpose is to run tasks. You give it tasks to run, and it chooses how it's going to do that. And of course, a special case of that is a thread pool. It says, I've got 5 threads, I'm going to run my task on here, you give me the tasks, I'll choose which thread does it. And then I'll keep reusing the threads to do multiple things. The basic requirements are simple. You might have to be able to copy them around like a handle, and then you must be able to call execute given a function. And if you have that as a basic level, you can build just about any form of complex processing to deal with those tasks. You can wait for them, you can support cancellation, you can put continuations on, all these things. But you might hope that the executor had some of those properties already. In which case, then you can query. And you can say, I want something that's going to give me a future back. And so you can ask it for two-way execution. And so that's going to give you a future back. And then you can use the new, know that you've safely got a new member function, two-way execute, that will give you a future. So like I said, when I introduced coroutines, I'm hoping, the C++ 20 standard has coroutines but has no library support. I'm hoping that there is going to be some library support coming soon. The idea would be that you have something like a task of T that you could return from your coroutine to say that it was intended to run as an async task. And then you could integrate that with executors, and it would, as your coroutine waited for other tasks, then those other tasks would be scheduled on the executor, and then your coroutine would be resumed when the tasks were ready. But that's not got a concrete proposal yet for coroutine support. That's just something that I would like to see and I know is possible. So over the next few years, I imagine that there will be proposals forthcoming. We also have some proposals for concurrent data structures. If you're sharing data between threads, then you're going to want to have some data structure to encapsulate that. Obviously, if you're sharing single values, synchronized value works quite well, but you might want more than that. We've got concrete proposals for standardization for queues and hash maps. And obviously, queues are an essential building block for lots of multi-threaded scenarios. If you're doing actors, you need a queue. If you've got thread pools, you need queues. If you've got pipelines, you need queues, all these things. Queues are a common building block, so it's great that we have proposals, but again, there's currently only proposals. They've been through SD1 a couple of times, but we haven't got them even in a TS yet. Likewise, concurrent hash maps are an incredibly important data structure that are used for lots of cross-thread synchronization, and we have a proposal for that. But again, there's lots of corner cases that people need to work out, so again, it's not yet in a TS, but we do have concrete proposals. So yeah, if you have a concrete queue of my data, then on one thread you can produce some data, and another thread you just call value pop to remove the value. Hash maps provide us fast lookup. And you would want a concurrent hash map specifically designed for those cases where putting a mutex around an unordered map will hurt your performance. So you would then need something that's been specially designed for concurrent access. Writing such a thing is really hard, and so we want the library to do it for us. So the final facilities that I'm going to cover are those we've got for safe memory reclamation, which would help us write these concurrent data structures. Fundamentally, lock-free algorithms need a way to delete data when they know that no other thread can now access it. You've removed an element from your concurrent queue, but the value itself was stored in some form of node because you needed next and previous pointers and things like that. So you want to delete your node object, even though you've safely removed the value from the queue. How do you know that it's safe to do so? This is what our safe memory reclamation schemes give us. We have two proposals for these. They both have different trade-offs, so it would be good to get both of them. The first is RCU, and the second is hazard pointers. RCU comes from the Linux kernel, but there are user space implementations. And the idea is that read sides are really, really cheap. In the Linux kernel, read side is completely free. There is literally no additional instructions generated. But in user space, then you have to have instructions, because you have to say, I'm starting my read now and I'm finishing my read now. And it puts the big cost of doing this safe cleanup on the side that needs to delete the nodes. unless you explicitly defer that to a background thread, which is also viable. Hazard pointers do essentially the same system, but in terms of what you can do with it, but it uses a completely different mechanism. Whereas RCU is about saying, I'm reading, and it doesn't specify what you're reading. With hazard pointers, you say, I am explicitly trying to read this object here, so I have a hazard pointer that refers to it. And so they provide a completely different set of performance trade-offs, and we have proposals for both of them. If you're actually interested in following the proposals, then here are the paper numbers. When the slides go up on the CppCon site, then these are links that you can click that will give you the papers. So we have paper numbers for all the different proposals. My book is now in print, the second edition. There are copies for sale. I'm very glad that it's finally in print. The Concurrency TS stuff that it covers actually includes latches and barriers, which are now in C++20. There is some stuff about joining threads, but it's not called JThread in the book because we changed the name after I'd written it. Semaphores are not covered because they were added to C++20 again after I wrote the text. And some of this stuff is in my JustThread Pro library, which including RCU and atomic shared pointer. And I will extend that to support the rest of C++20 synchronization and then some of the additional things from the proposals. Has anybody got any more questions?
Two comments and just one question. I had two, but you just answered the second. Thanks for a very nice presentation. I enjoyed it. And I can't wait for the new features, though I have to wait. I've been waiting for some of those for 10 years. And the simple question is, do you have any uses left for plain threads as opposed to JThreads?
Uses left for plain threads as opposed to JThreads. If you are not going to use the cooperative cancellation, then there is a tiny little bit of saving of data size because it doesn't have to construct the synchronizations for the stop token. And if you're going to detach your thread so you don't care about the automatic joining, then likewise, that doesn't gain you anything. But those are niche uses. For most people, I would imagine JThread is just a straightforward drop-in improvement over standard thread.
Thanks.
Any more? Yeah.
So I'm sort of looking for an equivalent of async where I don't care about the return value. Like I want to fire and forget. Is there such a thing? Or do I always have to create a new thread and detach?
So yes, that is one of the things that people don't like about standard async, which is that the future always waits for the task. So you can't fire and forget it. On the flip side, sometimes that's really useful. So no, it would be a shame to lose that. We don't currently have anything in C++20 that does anything like that other than spawning your own threads. For future things, then when we get executors, then some of those executors will allow us to spawn async tasks in some fashion, and obviously, and you won't have to wait for them because that's something that people really want to be able to do. So it's things that SG1 are discussing, but we haven't yet got any concrete things because we haven't nailed down executors. It's taken us 10 years to get this far and it's not done yet.
Okay, thank you.
Hi, I have a question. So do you know if any of the implementations are already available for Clang, GCC, or Microsoft?
So I don't think any of the major implementations currently ship any of these concurrency facilities. JThread is available on Nikolai Josutis' GitHub, along with stop token. So that should then work on all of these. The integration on that with condition variable, it's called condition variable NE2 because it's an add-on library, so it can't replace the underlying stuff. For everything else, for those bits that are covered by my library, it's the only implementation I'm aware of, but I don't cover everything. So, but it's, yeah, so hopefully the GCC and Clang teams will pick up the implementation shortly, and Microsoft. They are doing really well at getting the libraries up to date. So I'm hopeful that by the time C++20 really is officially stamped ISO C++20, we will have concrete implementations. But for now, there aren't any in the major providers.
Hi, do you know if there are any proposals for a concurrent priority queue?
I'm not aware of any, but that doesn't mean there aren't any that I haven't paid attention to. But yeah, I'm not aware of any.
So is there a plan to have scheduled execution on the, on the executors, so I can say execute at this time or in this many, whatever time unit?
That is certainly something that has been discussed. I am not sure whether people are planning to ship such a thing with, assume if executors got into C++23, there would be some standard provided executors, or whichever standard they first get into. I don't think that's likely to be one of them, but I'm not 100% sure, because obviously it's not there yet. But it's certainly something that's been discussed, and supporting such a thing is one of the things that people want to make sure that the model does support.
And the reason I'm asking is to implement something like, so in C# you would say task.delay, which is very similar to the proposal here with the futures in that. So will there be something where I can say, delay execution for a certain amount of time, so I can, do a when any either, delay expired or waiting for input or something like that, waiting for network?
Yeah, certainly there are benefits for being able to do so, and I imagine that if we don't provide directly the facilities to do so, we'll provide the building blocks that allow you to write such a thing.
Okay, thanks.
Hi, it's sort of an open-ended question, but I wanted to understand if there is any performance penalty for using atomics.
Well, okay, so performance penalty for using atomics, compared to what, is always the question when you're looking at performance. If you have an integer and a mutex and you are using that as an account, then replacing that with an atomic int is probably always a good plan. If, on the other hand, you're thinking using atomics to create a complicated lock-free data structure versus using a mutex and a simple single-threaded data structure, you need to profile. The complicated lock-free data structure will have a cost inherent in doing its atomic synchronization. But it might have, it will have different execution properties. If you use a mutex, then your threads, only one thread can access the data structure. If you've got a lock-free data structure, you might find that there is now concurrent access. But the best case or average case access with a mutex might be less than the average case with the lock-free data structure. So you need to look at what the trade-offs, measure what is important for your application, and sometimes there is a performance penalty and sometimes there is a performance improvement.
Thank you.
Okay, well, we're out of time, so let's stop there.